everyone, our group will do that risk student prediction. My name is Kun.
I'm Bree.
And I'm James.
So just to show us our background, we want to use the machine learning to predict if a student will drop out or not. And why this is important is because at UW, there 22% of students drop out after their first year. And nationwide, the dropout rate of the student is 28%. The US taxpayers spend nearly $2 billion annually on educating non-returning first-year students alone. And the machine learning can predict the student dropout, offer academic assistance to the students who are likely to drop out to reduce their chance to dropping out. And although the machine learning can predict the student dropout, the algorithm can be biased. Because in 2018, Amazon scrapped the AI recruiting tools that can be biased against the women. And the technique have been developed to predict student dropout, but none of them have considered the fairness in their predictions. We are also the first one to propose a fair random forest algorithm that can maintain the privacy of the student information. And we are the first one to show the intersectional bias is more likely to occur on the first few nodes of a tree.
So one important aspect to our project is fairness. So for our project, we're going to be looking at fairness between groups, meaning that we treat all groups equally. We treat male students as equally as female students, and for other demographic information. And then another thing we're looking at is intersectional bias. So that's bias that happens when we combine several attributes together. So in this example, you'll see that there's 5 blue and 5 green individuals circled. So based on color, we may think that it's a fair prediction. There's also 5 males circled and 5 females circled. So based on gender, we may think it's a fair prediction. It's only when we combine gender and color that we see that green males and blue females are discriminated against, since no individuals in that group end up being circled. So here's some of the major milestones that we kind of accomplished over our project. First, we completed a review of existing fairness literature to see what other methods had been proposed so we could propose some new methods. And then we acquired anonymous student data from the university to run our algorithm against. We developed the first distributed fair random forest, and then we showed that intersectional bias is more likely to occur in the first K levels of a tree. For our development environment, we just used Python, and then we used the popular scikit-learn package for all of our machine learning. And then we uploaded all of our code to share with each other via GitHub. And then here's a brief summary of some of our major roles. I mostly worked on developing the distributed fair random forest algorithm.
And I'm working on to build a detector to detect the intersectional bias.
And I work on the dataset collection with the university and running the tests on the dataset.
So here's an explanation for our distributed fair random forest algorithm. The first thing we need to explain is the randomly generated decision trees that our algorithm is based on. So in this diagram, we can see an example of a decision tree. The X's are just features for each student, and then the 1 and 0 would just be some threshold. So for example, the first feature may be if a student is engineering or not. If they are, we will go to the right path. If they're not, we'll go to the left path. And then we continue that for other features for those students. Once we follow that graph and we end up in a box, that's the prediction that we make for that student. So if we end up in a 1, we may predict that that student drops out. If we end up with a 0, we may predict that the student does not drop out. For our technique, we want to randomly generate these decision trees. So at each level, we just randomly pick several features to build our decision tree with. So here's just a longer explanation for our algorithm. So first, we assume that there's a third party that holds private demographic data. The reason we do this is because we want to maintain the individual privacy of this private student information. Then there's a data center that holds the other remaining student data and builds the model. Note that during the model building process, our algorithm never has direct access to any of the private demographic information for students. So first, our model builds randomly generated decision trees, and then we send those to the third party, which audits those for fairness. The trees that are fair are then sent back, and then we weight those trees based on accuracy so that we can make accurate but fair predictions. Here's some of our example of results. So on the left, we have air. Lower air means that we have a better prediction. The blue ridge model is our best weighted model. So you can see here that has quite low error. The lowest it's just as close to the non-fair random forest version. On the right is a measure of statistical parity, which is a measure of fairness. The lower the statistical parity, the more fair our algorithm is. We again note that our blue ridge weighted model achieves quite good fairness. I want to note that the red model is what would happen if we didn't weight our decision trees. While it is the most fair model, it's only the most fair because it just predicts that no students drop out. So it doesn't make any useful predictions, which is why it was so critical for us to weight our predictions so that we can achieve an accurate and fair model. Here are the results when we compare against other existing fair techniques. The DFRF algorithm is ours, and then we compare against 3 other techniques. You'll note that for our error rate, we achieve the second best error rate, right, very close to the best out of the group, but we also achieve the lowest statistical parity, meaning that we have the most fair prediction. I want to also note that our algorithm can't just be applied to student records, but it can also be applied to any machine learning task. So it's quite extendable as well.
So here is the second part of our project that I built an intersectional bias detector that's based on a standard decision tree. And this is a tree-based detector. In this tree, each parent node in one level will be splitted by one feature at a time. And this feature will be decided by calculating the label entropy of different features for each node. And then since each node, it has different sizes, so we then apply the weighted addition to add more weights on the smaller size, on the large size weight nodes, and then lower weights on the small size nodes, and then add them together, and then choose the feature with the smallest entropy. And then to limit the size of the tree and the size of each leaf node, then the tree will stop splitting until it reaches the maximum depth, or the leaf nodes are pure enough. The reason why we want to have this tree-based detector is we kind of want to have an easier pattern to allow people can easily and quickly define the intersectional bias if they only have a decision tree. So then we assume that in the decision tree detector, the top several features in the tree is more likely to show the intersectional bias than the bottom several features. And to prove that, we just basically calculate and compare the disparity between between each 2 features. And the disparity is the difference in dropout rate of each feature values for 1 or 2 features. So if the disparity is very high, that means these features are biased. To show the result, we use the color map to display the disparities. And so in ideal case, the color map will show a very smooth color change from the left bottom to the top right as the light color to dark color. And then we first tested with the University of Wyoming datasets, which includes about 1,572 students for 1 term. But since this dataset is very unbalanced, which has only 9.7% dropout rate, so it may happen in one case that when we split a parent node, it will have 2 child nodes, is very pure, and also have a same dropout rate. So that means this parent node is appear in the top of the tree, but the disparity of the 2 child nodes will be very small. So that is why in this result, it appeared the dark color appeared in the front of the light color. And then we tested the detector with a crime community data set. So this data set is kind of a balanced data set. It have a 40% high crime rate. So as you can see that at the top, about the top 12 features, the result almost satisfied our hypothesis that has a smooth color change from light to dark. But however, as we split the tree to the bottom, it will also have some internal nodes that are unbalanced data. So that is why on the bottom view features, it have some unsatisfied results. Here is a quick comparison between the standard decision tree versus our decision tree detector. So we both use the weighted entropy to split the parent node, but in standard decision tree, they allow to use the different features in one level, and each feature since can be reused more than once. But in our detector, the one level is use the same features, and each feature can only be used once. And here is a color map result for the standard decision tree for the university data sets. As you can see that this result is not as satisfied as our tree detector. So that means kind of means like our detector has a very good and great initial start to detect the intersectional bias. And then after that, we have some roadblocks for the project. So it actually took a long time to get access to the university datasets, especially later in the during the COVID-19 period. Everything becomes virtual. And also researching a new algorithms and method is difficult because we have to learn a lot of new things and read more research papers. And it is a very challenging task to prove a new method works because you have to do more testings and experiments. Some changes to our plan from beginning. So initially we was hoped to do both detect and remove intersectional bias. But then we noticed that it is already a very challenging task to just doing the detecting intersectional bias. So then we don't have more time to do the removings. And then before we was planning to do the transfer learning, which we can transfer the prediction from one university data to another universities. But also due to the time concern, and it is a very complicated task. So now we are no longer to do the transfer learning. Here are some COVID-19 impact. So the first one is we moved all the meetings to Zoom, and then we was hope to work more with the registrar, so kind of request more data and kind of show our algorithm to them. But due to the COVID-19, we don't have that time and we don't have that opportunity to work with them. And as I said before, it actually took us a longer time to accessing the university datasets because we have to set up the virtual access from our computers.
So there's a few lessons we learned. First, working with the universities can really take an extremely long time. And it's worthy to email the author of the paper we read, because James received help from an algorithm that we were implementing on the paper. And also running the experiments can take an extremely long time, especially on the large data set. And there's some future work which could make our project steady. These future works include making a good UI interface for this register office so they could easily use the algorithm. Also could improve a decision tree detector for the better results that satisfy the hypothesis. And also could investigate removing the intersectional bias. and also could design an algorithm that can apply to transfer learning data using one school data set to predict another school data set, student dropout rates with a higher persistence. Any questions? Please feel free to email us if you have any questions about our algorithm or result.